Having looked at the fact that we have circular motion in a magnetic field when we have a charge moving through it, let's look at one of the applications of the circular motion. This is a cyclotron, which is a particle accelerator. And you'll get about 10 MeV protons with a cyclotron. You have here your ion source. So between these two Ds, they are called, for obvious reasons. And these Ds are held at a PD to each other. It's an alternating PD, as you'll see in a moment. The Ds are sitting in this uniform magnetic field. Now I have chosen this field to be down through the Ds. I'm going to have some positive ions in my mind coming out of this ion source. So you have the ions coming out of the ion source. They're being accelerated by the electric field between the Ds here. Let's have this D positive and this one negative to begin with. So my ions are going to come out of here. They're going to be accelerated to the left. Using Fleming's left-hand rule, we have the field down the page. We have the positive ions being accelerated to the left. And so the force will be this way, towards me, out of the page. So my particle is going to perform a circle. Now when it gets back to here, this polarity needs to reverse so that this one is negative and this one is positive, so that the particle again, the ion, is being accelerated across the gap. The acceleration only occurs in the gap. Okay, this is where the acceleration is occurring. What you've got here, there is no electric field inside this hollow conductor. That's one of the laws of physics that we haven't talked about really, but it is true. Inside a hollow conductor, inside a hollow sphere, for example, there's no electric field. So there's no field in here, no electric field inside these Ds, which means there's no acceleration taking place in here linearly. Clearly, the particle is being made to curve, but there is no change in the magnitude of the velocity as it curves inside the Ds. What you do have is the electric field in the gap causing the acceleration as the particle comes across, accelerated initially, we said, from the right to the left, and then when it comes round here, the polarity of the Ds has to reverse so that it's being accelerated from left to right, and then back here we've got that process being repeated. So the acceleration takes place in the gap here, and of course that means that the frequency of the supply has to be right for that to happen, and we're going to come up with an expression for that frequency, and you'll see why there is a limit to the energy that can be supplied to the protons in a little bit. You'll see that there is a mass term in that expression, and if the particles are traveling too fast, then the mass increases due to relativity, and so the frequency of this supply can no longer be fixed. But we'll gloss over that a little bit as we get through the expression. So what we've got here then is some particle, charge Q, moving in a circle due to the field B. and it's being accelerated in the gaps between the D's. Eventually, the radius of the circle, of course, will increase as the particle travels faster, and the accelerated particles will come out of the D. There'll be a chute here. I wasn't able to draw the chute terribly well, but there'll be a chute here where the charged particles eventually will come out. Now these things are really very small. When I did this work at school, I imagined the D's to be something like the size of a football field. In fact, you could hold these in your hand. They're probably about 20-30 centimeters across diameter. There's one of these, the very first particle accelerator at CERN is in the CERN museum, and I was really quite underwhelmed when I saw that because it was so very small in comparison to my expectation. But this is not a big piece of equipment. So let's look then at that expression for the Let's look at the expression for the frequency of the supply. So, what we've said is we have a force equal to BVQ, where Q is the charge on our ion, V is the velocity of the ion, the speed of the ion, and B is the flux density. Now, we know this is moving in a circle, and so we know that this force is also equal to mv squared over r. So we can equate these two, and we can say BVQ equals mv squared over r. Now, if we then get an expression for V by rearranging this, then what we get is BQR over M. Now we also know that V is R omega, which is R times 2 pi over T, or R equal to 2 pi F. All right, from our circular motion work. So our period, if we put V equal to, put this in here, we've got 2 pi r over T equals BQR over M. We get an expression for T equal to 2 pi M over BQ. Or we could turn this upside down and we could say the frequency, which is 1 over the period, is BQ over 2 pi M. So that is the frequency of the main supply that we need. That's the frequency of the rotation of our particle. And so the supply is changing direction. So you have the particle comes across here, first half cycle, across here, second half cycle. PT has reversed, and then we're back to here again, first half cycle, back to here, second half cycle. So it is reversing here and here. All right, so that is the expression for the frequency of the supply required to accelerate this particle Q in this cyclotron. Now you can see here there is this mass expression, and at very high velocities, at relativistic velocities, velocities large fractions of the speed of light, mass increases. And so if the mass increases, then the frequency clearly has to change so that the acceleration occurs at the right times, at the right points in the oscillation. So it is no longer a cyclotron, but a synchrotron. Sorry. Or a cyclosynchrotron. We don't get into this, but this is the reason why there is a limit to the energy of the proton. If you think about the kinetic energy of your proton being a half mv squared, if you work out your kinetic energy in joules, take your 10 MeV, work that out in joules, stick that into a half mv squared using the mass of the proton there, you'll see that the velocity of the proton at that sort of energy is quite large, and as a consequence becomes relativistic beyond this, and you end up having to have your cyclosynchrotron rather than simply a cyclotron. Let's perform a calculation then to work out the frequency of the supply required. So let's consider an alpha particle. So we're going to have a positive ion here. The mass of that alpha particle, 6.72 times 10 to the minus 27 kilograms. Let's say this is in a region of uniform magnetic field, 0.66 Tesla. This is quite a strong field, but there are stronger. The radius of the orbit then is 0.7 meters. And the question is, what is the maximum Ke that this alpha particle can have, and the frequency of the supply? So if we go back to our equation for the velocity of our particle, we had an expression which was V is BQR over M. If we stick in our numbers, 0.66, the charge on this, of course, is 2 times 1.6 times 10 to the minus 19 times the radius, 0.7, divided by the mass, 6.72 times 10 to the minus 27. That gives us a velocity of 2.2 times 10 to the 7 meters per second. And Ke, of course, is a half mv squared. So if we stick our numbers in, squaring this, multiplying by the mass, then we get 1.6 times 10 to the minus 12 joules, or about 10 MeV. Now you can see this is about 6% of the speed of light. So it's quite big, and as a consequence, getting much bigger than that, you're going to get relativistic. It's going to start to look quite significant. and the mass will start to increase. And the frequency then, well, if we use our expression, which was BQ over 2 pi m, we get a frequency of 5 megahertz. That's a capital M.